Now taxes is 100% free when you file in the TurboTax app if you didn't file with us last year.
Oh, yeah?
Yeah, just do your own taxes in the app by 2/18.
What if I have lots of forms?
All good, all 100% free.
What if I had 3 jobs?
Still 100% free.
What if I once saw Bigfoot?
That has nothing to do with taxes, so still 100% free.
Now that's what I'm talking about.
Now this is taxes. See if you qualify in the TurboTax app. Excludes TurboTax Live, must start and file in app by 2/18.
Hi there. Thanks for joining us. This is Space Nuts. My name is Andrew Dunkley, your host. Great to have your company once again. Coming up on this episode, oh boy, it is jam-packed with rocks. We're talking rocks of all shapes and sizes, and one of them that might not even be a rock. But our first story will focus on a rock that is heading our way, and in 2032, according to the popular press, we're all doomed. But everyone else who looks at it scientifically is saying, well, maybe not. Another new asteroid has been discovered, and it can steer itself. We're also going to look at some rock samples. We're talking Osiris Rex. Some new information from that little mission, and a massive visitor in our deep, dark past may have disturbed our planets. How so? We'll tell you all about it on this episode of Space Nuts.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2.
1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
And Fred Watson is still away chasing beautiful skies. I've seen some of the photos Fred's taken of the Aurora Borealis during his sojourn north, and spectacular photos they are. So covering for Fred is Professor Jonti Horner, Professor of Astrophysics at the University of Southern Queensland. Jonti, hello.
Hey, how are you going?
I'm good. Welcome again. It's good to have your company.
Oh, thank you. It's always good to be the substitute Yorkshireman. So.
Yes. It's funny how that worked out, isn't it? Will we get straight into it? Because we've got a lot of rocks to sort out. I used to have a rock collection, but nothing like this. Our first story focuses on the Atlas survey, and they've spotted a rock that might be a threat in years ahead. Now, I need to make a confession. I spotted this story the other day when I was reading through some science information, and if I spot something that I think's worth talking about on Space Nuts, I'll send it to Fred. And in this case, I sent it to you and said, look, I don't know if this is kosher or if it's the popular press going nuts, but it's on a very well-respected platform, The Conversation, so I think it's got some credibility. Jonti emailed back and said, yes, I'd love to do this story. I was the author. I didn't read who the author was, but from now on, I'm going to do that. Very embarrassing for me, but yes. But yeah, I gave it credibility because it was in The Conversation. If it was on one of the other platforms that shall remain nameless, I might have been dubious. But not that being said, I think, in the time to come, when this rock's getting closer, the popular press will do the doomsday stories for sure. So what is this? Yes. What is the story behind this one?
I will just flag up briefly, actually, The Conversation is a very good, reputable place because it's introduced. It's an Australian initiative initially that was introduced more than a decade ago to address the fact that a lot of specialist journalists were getting laid off. And therefore, there were growing problems with fidelity of information in the mainstream media, stories getting misinterpreted, and scientists, as a result, getting quite anxious about talking to media. And The Conversation was set up with an editorial team who were professional journalists, whose job it is to get articles written for them and just help the authors write the articles. But the people who write the articles are discipline experts. So I won't say much about it because it's not what the podcast's about, but it's worth checking out for people because if you see an article in The Conversation, it's written by somebody who's an expert in that field and therefore should be giving you the true story, not necessarily the hyped story. So I'm a big advocate.
I'll give you an example of a hyped story that I read this morning, and this has got nothing to do with astronomy, but a certain well-known soccer player is in court. And all the popular press are dumping on this person because of a supposed racial slur. She's actually facing charges of breaking a window.
Yeah, there's a few things in that. So I come from the UK, so I've been following this as a football fan, and it's drunken, reprehensible behaviour, but a lot of people get drunk. Thing is, in the UK, though, if you are recorded saying anything that is racially motivated, particularly saying it to police officers, that's kind of unwise, and that's what's led to all of this.
Yes.
So it's led to a lot of interesting coverage and a lot of very interesting discussion on football forums around the place.
Yes, indeed. But I just thought it was a good example of them chiming in on, the juicy bit, but leaving out the fact that the arrest occurred as a consequence of malicious damage that was alleged.
Yes. And then the additional charges are being layering the arrest.
Yes.
Again, very off topic. We've been doing this 30 seconds. We've already gone on 2 tangents. So it's going to be a good episode.
So the Atlas survey and this rock that may or may not be hurtling towards Earth at some time in the not too distant future.
This is a story of an asteroid that goes by the name 2024 YR4. So these things always get essentially a barcode that tells you exactly when they were discovered. So the 2024 means it was discovered in 2024. The first letter always tells you which fortnight of the year it was discovered in. So A would be the first 2 weeks, B the second 2 weeks. In this case, Y means it was the last 2 weeks. So this was discovered on the 27th of December. Interestingly, 2 days after it had a close encounter with the Earth, we saw it as it was going away from us. Which tells you how hard these things are to spot.
Yeah,
we've now got just over a month's worth of observations of it, and it's kicked off as a story in the last week or so because those observations have allowed us to work out the orbit of the object. It goes around the sun just over every 4 years, which tells us that in 8 years' time, it's going to come perilously close to the Earth. And within the level of uncertainty of the orbit, there is a chance of it hitting the Earth. And if you go on the CNEOS Earth impact monitoring site for this object, you can actually check that probability out day by day, and every day it's changing. So when I wrote that article for the conversation last week, it was 1 in 77 chance. Over the weekend, it got as low as a 1 in 50 chance, and as of today, as we record, it's at about a 1 in 71 chance. And the reason that number's going up and down so quickly is because we're getting more observations. So the headline for this in a lot of the media has been, the global security protocols have been enacted. I can't remember the exact phrase, but everybody's at panic stations, and it's not quite that bad. But what's happened is that astronomers around the world have been alerted to this. They've been told that this is a target of priority. So all the telescopes around the world that can look at it are making extra time in their schedules to do so and get a lot of data. And what that data lets us do is refine our understanding of the orbit to better predict it forward in the future. And every 24 hours, they run an updated fit for the orbit. That gives you the parameters you see online, and that gives you this impact probability. And what the impact probability is really telling you is that on the date at which the impact could happen, which is the 22nd of December 2032, how big is the area in which this asteroid could be at the time it would hit us compared to the area of the Earth? So if you've got a 1 in 70 chance, it means the area of space the asteroid could be in is 70 times bigger than the cross-section of the Earth facing it, roughly.
Yep.
Now, we know the time of impact very, very accurately because it's as this object moves across our orbit, but exactly where it'll be left, right, up, down is the uncertain bit, and that's why there's this uncertainty. Now, we're not going to know unless we're very fortunate that this is definitely going to miss or definitely going to hit in the next few weeks. I think that's unlikely. It should be bright enough for us to follow with telescopes till about April, and then it'll be lost even with the biggest telescopes in the world. And that's part of why there's the urgency for these observations now. It'll then fly past the Earth again at a distance of about 8 million kilometers, so a hefty distance away, in 2028. And part of the reason to get all these observations now is to know exactly where it will be in 2028, so that we can do better follow-up there with more prep. And the key observations in 2028 will be radar observations. So bounce radar waves off it, get the signal back. And that it gives you an incredibly accurate position for the thing, which really helps you refine the orbit. But it'll also allow us to figure out the size and the shape of the object with real accuracy. And with those observations in 2028, I think by then we will know for definite whether it's going to hit or whether it's going to miss. But we'll also be able to predict where it's going to hit down to an accuracy of maybe 10 or 100 kilometers. So that's what those observations in 2028 will yield. And what we're doing at the minute is laying the groundwork, essentially. So that's the background.
Okay. So it's going to be another few years before we can get enough data to be more accurate, about 2032. I mean, how big is this thing?
Well, there is one possibility we might get data and be sure sooner than that. And that's if we find a pre-discovery image, but nobody's managed that yet. So if this thing goes around every 4 years, it will have been passed us every 4 years in the past as well. So there's a chance it might have been picked up and not noticed before. And as soon as you get that information, that hugely improves the orbit. So that could rule it out or rule it in very quickly. In terms of the size, we honestly don't know, but it's a caveated don't know. So what we measure with this object is the brightness of it in the sky, which is related to how much sunlight it's reflecting back to us. So if you imagine two objects that are identical sizes and one of them is more reflective, more shiny, then that one will look brighter to us. It'll reflect more light our way. Now, for this object, we know how bright it is, but we don't know how reflective it is. And so, therefore, we can estimate the size based on a guess at how reflective it is, but we don't know. And so we have a range of potential sizes. We think it's between 40 and 100 meters diameter, with the most likely size being 55 to 60 meters. But we won't know for sure until we get those radar observations in 4 years' time.
All right. So what kind of damage would a rock that size do?
There's two scenarios, basically. We have scenario one, which is the most likely, is that this is a rocky, rubbly object, like the thing that exploded over Chelyabinsk in 2013, or the thing that exploded over Siberia in 1908. And the majority of near-Earth asteroids are these kind of rubble piles, because rocky objects are more common than metal objects. If it's one of these rubble piles, it will not have the strength to get through the atmosphere intact, and so it will fall apart and detonate probably somewhere between 10, 20, 30 kilometers above the ground. It'll probably get deeper into the atmosphere than the Chelyabinsk impact did because it's bigger, essentially. Blow up nearer to the ground, and that'll create an airburst event. Now, the amount of energy dumped into the atmosphere will depend on the mass of the object, the size of the object, essentially. It is roughly, and because of how wide that size range is, this is a very rough estimate. It's comparable in size to the thing that happened that exploded over Tunguska in 1908. Right. That is probably the biggest impact on Earth. It's certainly the biggest impact in recorded modern history, but probably the biggest impact on a timescale of 1,000 years or so. That leveled an area of trees in Siberia of about 2,200 square kilometers, which is equivalent to the area of Greater Sydney. So you'd characterize that as being a city killer. It's a kind of thing where if it hit over a city, everybody in that city would have a really bad day. Now, what the Tunguska event showed us is that Earth is mainly empty space. We hang around as humans and we all gather together. So what that means is that an object like that hitting the Earth most of the time wouldn't cause any problems because it would hit over the ocean or it would hit in the wilderness. But the flip side of that is if the Tunguska event had happened 2 hours later, it would have happened over St. Petersburg and millions would have died.
Wow.
So that's the kind of size of object we're talking about here. If, on the flip side, it turned out that it's an iron object, the fragment of a core of an object in the asteroid belt that got big enough to differentiate out into separate layers like the Earth has a core, a mantle, and a crust, and then was smashed apart. There are objects out there like that, and the best example of the effect of something like that is found in the Arizona desert. It's called Meteor Crater or the Barringer Impact Crater. And I visited there a few years ago before COVID, and it's really spectacular. You're talking here about a hole in the ground about 1,400 meters across, a couple of 100 meters deep, a crater. And that crater was formed 50,000 years ago by the impact of an iron meteorite about 50 meters in diameter. So the same kind of size scale as the object we're talking about. So if this thing is a solid metallic object, which I should stress is the less likely option, it would make it through the atmosphere intact because it's stronger. It'd hit the ground and carve out a big crater. If it hit the ocean, it would carve that crater into the water, causing then water to slosh around and probably causing tsunami around the coasts. But it's still counted as being something that will be locally damaging rather than regionally or nationally damaging. So it's something to watch, something to be really interested in. But I'm not losing any sleep over the fact that if it hit us, it will be a huge catastrophe, because I think that is very unlikely unless we're very unfortunate.
Yeah, okay. So too early to say, but we'll be able to get more data together in a few years, maybe sooner if somebody did get an image of it at some stage, but that hasn't been determined yet. Okay. We'll revisit that story at some stage, I am sure. While we're talking asteroids, let's go on to this story, which made me laugh. And this is an asteroid that was discovered in January of this year, but it turns out that it's not what they initially thought it was.
Yes, and this is a recurring problem. Now, I've mentioned before that our use of space is a bit like the Wild West, that we've not had legislature and planning and organisation keeping up with the explosion in our use of space. The story here is that an amateur astronomer, I believe, detected a new asteroid in early January, and they were quickly scanning through all the old data. They found pre-discovery images from 2018 of this speck of light moving across the sky. So this thing got flagged as an asteroid. It got given an asteroid categorization of 2018 CX2, I think it was. And it was quickly calculated that this thing was on an orbit that could bring it within 150,000 kilometers of Earth, so it's flagged as a potentially hazardous asteroid. It was only a little bit later that people realized that actually the orbit of this thing matches perfectly with Elon Musk's sports car that he decided to launch as a publicity stunt back in 2018. It's a Tesla Roadster that has been floating around on this elongated orbit that brings it near the Earth. And it got misidentified. So they put out a press release saying that we now know what it was. We're retiring that categorization. It is not an asteroid. Don't panic. But it's not the first time this has happened. It's certainly not the last time it's happened. We keep getting human debris and detritus being picked up and identified as asteroids. People go back, they go through catalogued observations, identify this in previous photos, you get an orbit, and it distracts a large amount of time from people who are doing the work looking for things like YR4, for objects that could pose a threat. And there's a number of issues around it. Now, part of it is that there is no rules or regulations in place for people who launch things to space to keep track of them or to tell anybody else what they've launched and where the bits are. Yeah. So we've seen these kind of stories in the past for satellites and space observatories. We've also seen it for spent rocket casings and things like that. Now, that's a little bit of a problem when you're looking at managing the impact threat to Earth from asteroids, but it's also a problem in terms of other people wanting to send missions out there. And Jonathan McDowell, who's really one of the world experts in space flight, space travel, and monitoring these things, has made a point that if you're flying on Earth and you're in an aircraft, you have to log a flight plan. You have to tell people where you're going when you're traveling as an aircraft safety thing so that planes don't meet each other, not expecting the other one to be there, essentially. He says, and this is a direct quote from him in an article here, if you have to file a flight plan for a local flight on Earth, you should have to file a flight plan for an interplanetary flight. Because you're going to get the same kind of things. The airspace is going to become more and more crowded. And it's a safety issue and a management issue. But there are just currently no rules and no regulations around this out there. And the tracking problem is particularly important because you've got to remember that NASA, JPL, the astronomy community as a whole, are keeping track of all the objects we know of in the solar system. And we currently know of nearly 1.5 million objects that they're tracking. So when you find a new object, it's not really straightforward to say, well, I remember Elon launched a car. Maybe it could be that. Let's check it out. Elon has not been tracking it and telling us where it is. So it is a real problem, and it's a big enough issue that people are flagging it up in the astronomy community. And it's another of these many facets of that balance between wanting to encourage the commercial use of space. And we've seen such incredible innovation in there, the reduction of the cost of launching to space, all the rest of it. But at the same time, you want it to be managed in a way that makes it sustainable and safe for everybody, rather than having companies essentially having free rein to do what they want. And so it's a challenging time, and this is just another of those issues that talk about transparency versus privacy, that talk about the right for companies to do what they want rather than regulation. But it's an interesting one, you know, and at the end of the day, if you launch your sports cars into space, you should have to track them.
Yes, it was a very expensive exercise, but I think you can afford it. But didn't they lose it at one stage? So this is basically saying, well, we found it again.
Yeah, well, of course they lost it. This is something the size of a car that goes on an orbit beyond the orbit of Mars. With the best will in the world, even the biggest telescopes on Earth cannot track the Tesla Roadster in its entire orbit around the sun, but nor should they waste their time having to do so when they could be looking for things that pose a threat to us.
Well, I think he's got his money back in car sales. It was a brilliant publicity stunt. He should have done it on April Fool's Day. That would have made it even more fun. Yeah. But yes, okay. So now we know it's not an asteroid. So they've had to unname it, basically. All right. That's a fun story. You can find that on space.com. And the previous story about that 2032 rock is on the Conversation website, written by none other than Professor Jonti Horner. This is Space Nuts. Andrew Dunkley here with Professor Jonti Horner. Time to take a short break to tell you about our sponsor, NordVPN. And they've got a great New Year deal for you, which I'll get to soon. Now, if you're someone who uses public Wi-Fi, then you could be exposed to hackers. And I'm talking about places like cafes, airports, hotels, shopping malls, anywhere that Wi-Fi exists for open use, basically. And let's be realistic, there aren't many places that don't offer it these days. Now, you might not be aware of this, but there are two ways hackers work. They can hack into your device directly, or they can intercept your Wi-Fi data, which could include your passwords and usernames. And once they get that, all bets are off. So what can you do to ensure your safety? Simple. Put up a wall known as a virtual private network, or VPN. This is software that makes you untraceable and therefore unhackable, and there's none better than NordVPN. As a Space Nuts listener, we have a special New Year offer available to you. Just go to nordvpn.com/spacenuts. That's nordvpn.com/spacenuts and click on Get the Deal and check out what's on offer through their monthly, yearly or 2-year plans. And the longer you sign up, the lower the overall price, plus an extra 4 months free. And of course, their 30-day money-back guarantee. And don't forget all their other amazing tools like cloud storage, threat protection, anti-malware. My favourite is the password manager, makes life so much easier. All available depending on which plan you choose. It's inexpensive, simple to set up, and you can use it on 10 devices through most operating systems, which is very impressive. Check it out today at nordvpn.com/spacenuts. That's nordvpn.com/spacenuts and click on Get the Deal. You won't be disappointed.
Roger, you're loud and clear here also.
Space Nuts.
Not quite, Professor Fred Watson. Not quite. It is Professor Jonti Horner. Fred's still away, and he should be back in a few weeks. We're still talking asteroids, Jonti, and this one we've spoken about many times because this was a really exciting mission, the Osiris Rex mission that got samples from Bennu. It was Bennu, wasn't it? And they returned to Earth safely, which was all very exciting. But now they've had a chance to, analyze this stuff, and it's been rather revealing.
Yeah, so one of the reasons that Bennu was targeted is the suspicion that it's a fairly pristine object. It's one of these near-Earth asteroids floating around, but based on observations of it going back a long time, the suspicion was that it's a kind of asteroid you call carbonaceous chondrite material. So it's old and in theory fairly pristine. And NASA sent the Osiris Rex mission there, touched down, gathered a huge amount of samples, more than twice as much as they were expecting to bring back, which amounted to them bringing more than 100 grams of asteroid material back to the Earth. Now, this is the third time that somebody has visited an asteroid and brought samples back, of course. The Japanese have done it twice successfully before with the wonderful Hayabusa and Hayabusa 2 missions. But this mission to Bennu brought back a lot more material. And it's taken a while for the results to kind of creep out from that debris that has been brought back. People have been analysing it, working really hard. Should be said they've actually quarantined off, I think, 60 grams of it to be held in storage for future researchers with better technology in the future. Just the same, incidentally, as the Apollo samples that were brought back by the Apollo missions, the Apollo astronauts. There are some of those that have still not been cracked open because they're preserved for future generations, which I think is brilliant.
Yeah, it's a great idea.
So what they've been doing with the Bennu samples is learning more about them. And we've suddenly had this raft of new results presented over the last few weeks, all discussing the findings from Bennu. And they are really interesting in the context of the origin of life on Earth and how common life might be in the cosmos. Now, with Bennu being really pristine and ancient, it's not been altered, it's not been weathered to any great extent, but it's an object that we know in the past was wet and warm because it's got clay type of materials on it. And what that tells us is that the asteroid we call Bennu was once part of a much bigger asteroid that was a kind of environment where temperatures and pressures got hot enough for liquid water for at least some time. That's why you've got these clayey type materials on it. In the analysis of the samples that have come back, they've found a lot of things that kind of reaffirm the idea that the building blocks for life on Earth could have been delivered by asteroids like Bennu, impacting the Earth late in the Earth's formation. So the kind of real headline news story here is that they have found 14 different amino acids in the debris they brought back. And the reminder is that on Earth, there are 20 amino acids in total that create all the proteins that we use. So they found 14 of them, 70% of them in this one set of samples. You brought back 100 and a bit grams of an asteroid, and you found 70% of all the amino acids used in Earth. That's pretty amazing.
Yeah.
They also say that they've got, I think it was all 5 nuclear bases that are used in DNA have been found in these samples as well as a very high level of ammonia. And ammonia is something that's often invoked in discussions of the origin of life. So this is, in theory, telling us a couple of things. It's telling us that these things which are viewed as being part of that primordial soup that gave birth to life on Earth could have been delivered from beyond, could have been delivered from asteroids. But it's also telling us that they're common in the cosmos. Because for us to just go and visit an asteroid and bring back 100 grams and find all these things tells you they're not rare. If they were rare, we wouldn't have found them yet. So I think that's really interesting. And it shows the value of going there. The other thing, though, that is buried kind of deep down in the article here that I thought was really interesting is the other value of going there directly. So on Earth, there's this weird thing with life to do with chirality, so the handedness of molecules. So when you've got molecules that form a spiral, they can be left-handed or right-handed, which direction the spiral goes, essentially. Now on Earth, all life seems to use the left-handed stuff. That's my understanding, the left-handed chirality. And historically, when people have looked at meteorites that have been found on the Earth and looked at the molecules in them, these long-chain molecules, they found a preference for those meteorites to also contain left-handed over right-handed chirality. So there's always been some suggestion that that left-handed preference comes from the material brought to us. But there's always been a bit of skepticism because the things that you find on Earth have been sitting on the Earth for a long time, so we're naturally contaminated. So it's why, for example, if we find a meteorite on Earth that we don't know how long it's been here and find evidence that it has been altered by water, we can't say that it was altered by water before it got to the Earth because the Earth's fairly wet. It's the same kind of idea.
Yeah.
So that's been a hypothesis floating around for quite a long time. But in order to rule out the earthly contamination side of things, you've got to actually get samples that have not been contaminated on Earth. And that's what these samples from Bennu have given us, because we've gone there and collected them and brought them back and kept them very clean and very separate from the local environment. And what it turns out in the new results from Bennu is that there is no preference for the left-handedness. You've got an equal amount of right-handed and left-handed material. So what that's suggesting is that the left-handed material is a result of the Earth rather than it being something the asteroids are bringing to us, if that makes sense.
Yes, I get it. It's pretty exciting because, and I think I said this a week or two back, or maybe the last 2 episodes, that I believe the recipe for life exists everywhere, and it's just a matter of, getting the right oven temperature, and boom, it flourishes. I firmly believe, like we mentioned it earlier, there was a time where we just did not know that there were other planets beyond our own solar system, and now we've found thousands. It stands to reason that the same situation exists for life. Not intelligent life, but life of some kind.
I mean, some would argue that if you watch the news, you'd wonder whether there's intelligent life on Earth and off Earth. And yeah, I'm kind of with you. I've met a very small number of people who think that life is a uniquely Earth phenomenon. And they're quite often biologists. And the argument they've made is essentially that life is impossible. We're a fluke. because no experiments have ever done have replicated life. It's too hard to generate. Therefore, we must be alone in the universe. But if you make life even slightly easier to have happen than that, even a tiny little bit, there's just so much real estate out there that life must be out there in the universe somewhere else. And that's before you bring into discussion things like panspermia, which we talked about in recent weeks, which is essentially life having the ability to infect other places.
Yeah, exactly. And I think that situation exists. And it's not just somewhere else out in the universe. There's potential for life within our solar system on the ice moons.
All over the place. And it's another of those science revolutions we've lived through, which is when I was a kid, we were still in the domain of life is not going to be found anywhere else than Earth. You know, you don't talk about life elsewhere. That's a bit kind of quirky in sci-fi. So pendulum had swung very heavily that way. But we started to learn about objects in the outer solar system. And one of the reasons that people have always argued that life would be scarce is that liquid water is scarce. Because at a first pass, the Earth's the only place with liquid water. We need liquid water for life. Ergo, life is very rare. But over the last couple of decades, what we've realized is that liquid water is actually everywhere in the solar system. Water itself is one of the most common things in the universe because it's what you get when you put the most common atoms, hydrogen, with the third most common atoms, oxygen. Hydrogen is 74% of all atoms in the universe. Oxygen is 1% of all atoms. You put them together and you get water. So the great bulk of the solid material in the outer solar system is solid water, water ice. But what we've found over the last couple of decades is that liquid water is everywhere. You know, we talked about Europa, which is a kind of standard bearer for this in the outer solar system. But the more we've studied the icy moons of Jupiter and Saturn, the more evidence we get that many of those moons have subsurface oceans. Some of the objects like the centaurs that I love, these small, couple of 100-kilometer scale icy bodies in the outer solar system, they're big enough they probably had liquid centers at one point. There may even be a liquid water ocean buried beneath Pluto. It's just everywhere. And with that much real estate, it's very hard to imagine that we're the only place that life has become established.
Yes. As Fred has said to us many times, the leap to more complex life forms is huge, but basic life forms, very much a possibility. I firmly believe that, and I think common sense is starting to send people down that road. Anyway, that's a fascinating story about Bennu. If you'd like to look it up, it's all over the internet, but space.com again is a pretty good place to check it out. This is Space Nuts. Andrew Dunkley here with Professor Jonti Horner.
0G, and I feel fine.
Space Nuts.
Our final story, Jonti, takes us to another object that passed through our solar system a long, long time ago in a galaxy not so far away. And it may have disrupted some of our planets. Now, this got me to thinking. We've found a lot of solar systems in our searches for exoplanets, and we've been mystified by the fact that a lot of them just don't look anything like ours, and we've wondered why. In fact, ours seems to be different from most. Could this be the reason?
Possibly. Now, I think a take-home we've learned from the exoplanet era so far is that every planetary system's unique, and it's a bit like every person you meet's unique because they've got their own unique lived experience. And every planetary system forms from a unique set of circumstances and experiences unique events through their evolution, so everyone will look naturally different. What we've tried to do in solar system astronomy for basically as long as people have been doing solar system astronomy is understand where we come from. So how did the solar system get to look like it currently does? How did it form? How did it evolve? Now, the events that led to this happened 4 billion years and more ago. So we're trying to solve a very distant crime by looking at the clues that are there today. So it's a bit like when you're driving along the highway and you see a little bit of glass on the road and a little bit of a ding in the barrier. You can infer that somebody's had a bit of an ups moment, but you don't know what kind of car it was. You don't know what the story was. So you've got to try and piece it together. And I'm sure the accident people will look at the skid marks and all the rest of it. Now, in the solar system, we have a huge number of objects. We mentioned earlier on, more than almost 1.5 million objects in the solar system that we know. And we see where those objects are and where they aren't. We see what their orbits are like. We see what they're made of. And we have all of those things as evidence of the processes that have led to now. And there are puzzles. We don't have any models of solar system formation that perfectly replicate what we see. Because of this chaos, the chaoticity, the lots of random events that can contribute. Now, people have suggested for a long time that there could have been a close encounter between the sun and a passing star or passing brown dwarf that sculpted our solar system, and a lot of that discussion has come from the Edgeworth Kuiper belt, this belt of objects beyond the orbit of Neptune that's like an icy analogue to the asteroid belt. And the outer edge to that is quite sharp and distinct. So could that have been sculpted by a passing star scouring the outer edge of the solar disk away? For example, we have discussions of Planet 9 based on some of those distant objects that are moving on orbits that are hard to otherwise explain. So this is that kind of game that astronomers are playing all the time, which is how do we explain the oddities? How do we get to an understanding of how we got to where we are now, based on our best models of the generalities of how planetary systems form? And that's where this work comes in. So we know a lot about the orbits of the planets. And one of the things we know is that, to first order, if you draw the solar system on a bit of paper, you're not far wrong. The orbits of the planets all move in pretty much the same plane, but they're not perfectly aligned. They're tilted to one another by a few degrees. Mercury is tilted by about 7 degrees, for example, with the biggest tilt. The orbits are not perfectly circular. They're all spread out in a specific way. Now, there's been a lot of studies in the past looking at the migration of the planets, how they've moved over time from forming in one place to living in another. And Renu Malhotra, who's one of the greats of solar system dynamics, was one of the first people to discuss this back in the early 90s, when she did work looking at the orbit of Pluto and inferring from that that Neptune must have formed closer to the sun than it currently is, and then it migrated outwards, pushing Pluto with it. And that is now just established scientific canon. That is an explanation that works. It fits with all the other objects we've found out there. And it was incredibly insightful and brilliant work 33 years ago when she first identified this and modeled it and showed it to be the case. Now, the reason I mention Renu Malhotra is that her latest work is what is the interesting story today. She's looked at the oddities of the orbits of the planets, both the terrestrial planets and the giant planets, and asked the question, what could have caused this? To answer that, she looked at the idea with her team that the solar system is moving through a galaxy where there are lots of other stars and lots of smaller objects, lots of brown dwarfs, lots of planets. And particularly in the environment where the sun formed, there were lots of other things forming. So you have a higher chance of close encounters. And so she said, what if there had been a close encounter? Let's run a huge number of simulations. I think she ran more than 50,000 individual simulations, all running for more than 20 million years, where in each simulation, she had the solar system and an interloper, an object flying through, not bound, not gravitationally held by the sun, but just passing through, where you change the mass of that, you go from something the mass of the sun all the way down to something the mass of Jupiter, and you change the trajectory, the speed it's coming through and how close it gets and how tilted that trajectory is. And the question is, can any of these scenarios provide a result that looks like the solar system we see today? In other words, could this be an explanation for what we see? And the result is yes. A large number of the scenarios led to systems that looked very similar to our own, particularly scenarios with less massive objects penetrating really deep into the solar system. So not a one solar mass star passing at 100 AU, but objects comparably mass to and a bit bigger than Jupiter, passing through the domain of the planets. And this can do a really good job of fitting what we see of the current orbits of the planets. The best scenario they found, the one that was the closest fit to what we observe today in their simulations, was a planet the mass of 8 Jupiters. So that's a massive planet, but not yet a brown dwarf. It's still a big planet, passing through the solar system with the closest approach to the sun of 1.69 AU. So that's just outside the current orbit of Mars. And that individual simulation was the one that resulted in a planetary system that looked the most like our solar system. Now, it's not saying that's what happened, but rather it's demonstrating that this idea, this hypothesis, can work to explain everything we see today. Now, the next step for work like this is to make predictions. So if this kind of model was the case, if this is what really happened, what will we observe in the coming years that corroborate that? What would it predict? And it's a wonderful time to do work like this because we've got the Vera Rubin Observatory coming online in the next year or two, which is the most ridiculous astronomical telescope ever built. It's got a main mirror about 8.5 meters across, but it's like a super, super fast camera lens, except 8.5 meters across. So it'll image an area of the sky 81 times bigger than the full moon every 10 or 15 seconds, letting it survey the entirety of the night sky once per week forever and evermore.
Wow.
Detecting objects up to 1 billion times fainter than we see with the naked eye. So the predictions are that Vera Rubin in the first year of observation will detect a number of objects that will increase the amount of stuff we know in the solar system by a factor of 10 to 100 times. So from 1.5 million objects, we'll go to 15 or 150 million objects. And that'll be a huge raft of new information, new clues for the detectives to use to try and solve that crime, to try and fit to the different models of planet formation. So it's a perfect time to do work like this, because you can say this is what we should see with Vera Rubin. And if this model is actually true, we'll find a lot more evidence for it in the coming years. So it's really exciting work and a really exciting time to be doing it.
Yes, indeed. Yeah. And just quickly, this object, what could it have been? Just another gas giant or a brown dwarf?
Describe it as a rogue planet. So if it's 8 times the mass of Jupiter, it counts as a planet rather than a brown dwarf. Now, this is, I suspect, eventually going to become a little bit of a bone of contention because of it being how we classify things. So the boundary between planet and brown dwarf is currently set purely based on the mass of the object, not actually on how they form. But the idea here is that if you form with more than about 13 times the mass of Jupiter, the temperature and pressure in your core will get high enough for you to temporarily undergo deuterium burning fusion, to turn deuterium into helium. And that'll be short-lived because there's not much deuterium there, but that means you're something that isn't a planet. In actuality, where that line sits depends a little bit on what you're made of and how you formed. But at the minute, it's good enough. But I still think you've got an interesting thing of the standard model of planet formation is you form through this thing called core accretion. You gather a load of rocky material and metallic and icy material first, and eventually get massive enough to hoover up gas.
Yeah.
You've then got a model that is instability, where gas just smushes together and forms something, and that will often form brown dwarfs and stars. If you find something that's 8 times Jupiter's mass, but it formed without a core, would it not be fairer to call that a brown dwarf? If you find something 20 times Jupiter's mass, but it formed like Jupiter did, is it not fairer to call that a planet? And so there's going to be a friction at some point between a size-based classification scheme or a mass-based classification scheme, and one that's based on the phenomenology, the kind of formation mechanism, the structure of the object. And I'm sure that'll be a discussion that'll be had in a few years when we start finding more objects in this overlap region, essentially.
Yes, and we should point out that this paper has yet to be peer-reviewed, but it has been put in the, is it the ARXIV? Is that how you pronounce it?
So archive, ARXIV. Now, this is it's well worth everybody knowing about, actually, because most astronomers and most researchers in all related fields of astronomy, when we get a paper accepted or when we submit it, and which of those thresholds it is depends on your subdiscipline in astronomy quite often, we'll put a paper up in an unformatted, not in the journal format version on the archive so that it's freely available for anybody to download and comment on. And this is a resource that's been there for decades, to be honest. So what it means is that even if you have a paper that's published and is behind a paywall and you can't get to it, the likelihood is you'll be able to find a copy of it on the archive for free. And my suspicion is that this paper has been put up there. It's Garrett Brown, Renu Malhotra, and Hannah Ryan, all of whom are very well regarded, very reputable scientists. I suspect they've put it up there whilst it is under peer review to just get a bit more feedback. So there are people doing that now. Get more of their colleagues to reach out and say, oh, this is brilliant. Have you considered X, Y, Z? And it usually leads to a stronger paper in the end.
Okay, so if you do want to check it out, it's on the archive.org website, which is spelled ARXIV.org, just to confuse us even more. Or space.com. That's always a good source of information. And that wraps up another program. Jonti, thank you so much.
It's an absolute pleasure. Thank you for having me.
Oh, it's always good, always good. And don't forget to visit our website between episodes. You can do that at spacenutspodcast.com or spacenuts.io, and you can listen to back episodes of the show. You can visit the Astronomy Daily newsfeed and sign up for that, so you can just keep getting astronomy information in your inbox. There's a supporter button if you're interested in doing that. We would never force you to do anything like that, but if you're interested, please check that out. And thank you to all those people who have voluntarily subscribed to Space Nuts. We certainly do appreciate your support. That's just about it. Oh, Hugh in the studio couldn't be with us today because apparently what he did was he put on a spacesuit and was last seen heading out of the solar system in a Tesla Roadster. And from me, Andrew Dunkley, thanks for your company. We'll see you on the very next episode of Space Nuts. Bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Available at Apple Podcasts, Spotify, iHeartRadio, or your favorite podcast player. You can also stream on demand at Bytes.com.
This has been another quality podcast production from Bytes.com.